And welcome to this video. At this point, we will be working on another problem on uniform circular motion, but at this point, it's still on a horizontal circular motion. So the axis is on the horizontal axis. And at this point, it is what we call the rotator problem, where it's going to be fun if there is really a ride like this that you could experience, and that is going inside this cylinder. So it's made out of a cylinder. Okay? There's an opening, you go inside, and then the rotator will spin fast. Okay, so will it spin? Well, in this case, it's spinning at a clockwise motion. And as soon as it reaches that speed, maximum speed, you will be pinned on the wall. Okay, so hard. So just imagine when you are on those dryer, top load dryer, and then or washer, and then before you can actually take off your clothes and put it in the dryer, you would notice that most of your clothes are on the side. It's because of the same concept. Okay, so as it spins, it pins. Well, as it spins, and then it will pin the object, it will pin the person on the wall, and because of that force, creating a force that is pushing to the wall, and the wall is pushing that person that is on the wall, and then suddenly the floor will open and you will not fall down. Okay, you will not fall down. It would be interesting if we have, let's say, a fire underneath. Let's see if how safe it is being there, or maybe put some crocodile or some lions or tigers and deadly or poisonous snakes, as that will be excitement to us. Okay, so what is it that's preventing this rider, which is a boy with a mass m, okay, and as soon as it reaches the velocity with a certain radius r, okay, so in this concept, what do you think prevents it from falling? Okay, so we all know because of that force, okay, force and force. So dynamics. So as it spins, again, just like when I mentioned earlier, it will push you outwards, and because of the wall, it will prevent you from pushing away. Okay, so prevents you from pushing away, and now you have two forces acting on you, and that's why you are stuck on the wall. But because of another force called gravity, there should be something that will prevent you from falling. Okay? So there should be something that will prevent you from falling. Unfortunately, our illustration is colored ink or black ink. So it's really hard to see our section. However, we still can draw this one. This is your x-axis and this is your y-axis. Okay. So at this point, you need to think about what we have learned in the past or from the previous video in order to come up with an explanation. Why is it that you don't fall? Okay. If because of the speed that causes you to go to the wall and be pinned on the wall, and the wall is preventing you from escaping within the cylinder. Now, a force against a force, so Newton's third law of motion, basically you have what we call a normal force here. Okay? So the wall is pushing you back, while because of rotation, okay, you are being pinned, you're being pushed outward, and an action equal opposite reaction. That is Newton's third law of motion. Then this one is basically a normal force, since it's a wall, based on the definition of normal force. But now you have force of gravity that is pulling you downward. So let's say that is your... So right here, we can draw an arrow with a red. So that is your force of gravity. What is preventing you from falling, even though the floor doesn't exist anymore if it opens? Okay. So you're on the surface. There's a wall on your back. Okay. And we all know that the walls are not smooth. Okay. So therefore, there is something from preventing you going down. Maybe they put some double-sided tape. But in our case, there's no double-sided tape. And so there's equal amount of force keeping you from falling. Or that force is strong enough to hold you. Okay? strong enough to hold you, so you will not go down as being affected by force of gravity. Okay, so at this point, it is really nice to see if how are we going to solve this kind of problems, which is called rotator. Now, free body diagram, again, I mentioned earlier that there are some forces acting on you. Okay, so there's forces acting. Okay? So there is a force there. Okay, there's a force in it that is preventing you from falling. Okay, so there's a force right there that is preventing you from falling. Okay, and that force is force of friction. If I do have, okay, if I do have my force of gravity, which is also known as our weight, there is an equal amount of force in opposite direction. So that's 3, 5, 3, and then 5. So this will be our force of friction because you're pinned, okay? So you are being pinned on the wall, okay? So you're pinned on the wall. Now, where's the direction of the normal force? Okay, the normal force, as you want to go out, the normal force is preventing you from going out. In the previous example, we have friction on the surface of the rotating disc and the coin. On a conical pendulum, we have the tension of the string. Here, instead of using tension or friction, we are being pushed back by what we call the normal force from the wall of the cylinder. The normal force from the wall of the cylinder. Going further, let's use our blue ink. We can say that there is an acceleration going to the center, and that acceleration is called our centripetal acceleration. And as drawn over there, velocity is perpendicular to the center. So that's our velocity v, tangential velocity. Okay, so you were given the tangential velocity and all those good information. So now this is our free body diagram. Okay, so as you analyze the dot, you are being prevented to move up and down. Okay, so up and down. So what prevents you from moving up and down? Yes, okay, same amount of friction, same amount of force of gravity. So it will keep you at the same point, or there's no change in the state of motion, also known as zero acceleration. So now we can write down that the summation of forces along the y-axis, again for this case, for that dot, is simply equal 0 because that's the objective of the rotator. You will enjoy the spinning ride without falling towards the ground. If there's some alligators underneath, if there's some poisonous snakes, there's tigers, lions, or even fire, that's an open pit fire, that will be a challenge if we don't stay at where we are. Summation of forces. Now, forces along the x-axis, if you notice, or the net force along the x-axis, is being affected by the motion because the rotation is on the horizontal axis. Again, it's the horizontal axis where the axis of rotation is. Therefore, the acceleration is the centripetal acceleration. So in our x-axis, all the forces is affected by the centripetal force. However, in our y-axis, all forces are not affected by any acceleration or change in state of motion. In the past, we all know that force of gravity is equivalent to mass times g. The force of friction is simply the coefficient of friction multiplied by the normal force. Okay? So multiplied by the normal force. Okay, so at this point, let us calculate the centripetal acceleration, which is letter B. For letter B, I would want to use my blue pen. For letter B, what is centripetal acceleration? If you look at the question, you have your radius, you have your velocity. So also, I almost forgot to write it down. The velocity is 2 pi multiplied by the radius divided by t, the period. And then the centripetal acceleration is v squared over r. So for letter B, you are being asked to calculate the centripetal acceleration. And in this case, our centripetal acceleration is AC v squared over r. Basically, since you are provided with the velocity, you are provided with the radius, then that's your centripetal acceleration. So letter C, determine the normal force exerted by the boy on the wall of the cylinder due to the rotation. So as I mentioned earlier, as the boy is being pushed to the side, the wall exerts a force called the normal force. So before we start with the normal force, why don't we just analyze the different forces acting along the y-axis first? Okay. So forces acting on the y-axis is 0. So summation of forces along the y-axis is 0. Okay. Positive going up, negative going down. So we have positive force of friction, negative force of gravity equals 0. Or at this point, we can say that the force of friction is equivalent to force of gravity. So at this point, we have a different equivalent value for Fg, not only normal force. It depends on the illustration. Okay, it depends on the illustration. Now, the summation of forces along the x-axis is equivalent to mass and the centripetal acceleration. So what are the different forces acting on the x-axis? As if you look at your free body diagram, there's only one force, and that is the normal force exerted by the wall. And if I will write the normal force, is it positive or negative? For sure, it will be negative because it's towards the direction of the acceleration. So therefore, normal force is positive multiplied by mass times the centripetal acceleration. So therefore, letter C, we already have our answer. The normal force is equivalent to mass times the centripetal acceleration, not the acceleration due to gravity. In the past, we say that normal force is simply equivalent to m times g. But this time, because it's rotating, okay, it's rotating and the force is within or along the axis of rotation. So therefore, it is the acceleration due to the rotation or centripetal acceleration. Or we can also place this in terms of AC. So we can further simplify it, which means that your normal force is simply equivalent to mass times the square of the velocity over r, and that is your normal force. At this point, we don't need this one yet, but it's nice that we already analyzed the forces, so when we proceed to the next step, it's way faster. Now, let's solve for the last part, which is part D. Part D. Okay, part D. Now, this time, determine the coefficient of friction between the boy and the wall of a cylinder. Okay, so from letter C, we all know that the force of friction is equivalent to Fg. And that coefficient of friction is mu, or force of friction is mu, which is the coefficient of friction, multiplied by the normal force, equivalent to Fg is simply the same mass multiplied by G. Another step that we need to do is to divide both sides by the normal force, which will give us mu is your mass G over the normal force. So if you stop here, that's already given, but we all know that Fn, there is another value, which is mv squared over r. So mu, by replacing the value of your normal force, which is mass G, mass multiplied by the square of r. So my masses cancels. So now I have this as my answer, which is r divided by the square of the velocity. So in case you are being asked to solve for the coefficient of friction between the wall, then it should be the radius divided by the square of the velocity. Okay, so this is the maximum velocity. Okay, so maximum velocity. Now, if you want to figure out the maximum velocity, let's say I wanted to add letter E plus letter E. What is the maximum velocity or the minimum velocity? What is the minimum velocity for you not to fall? Okay, so how do you figure out the minimum velocity? Using your answer from letter D, which is mu r v squared. So all we have to do is replace or manipulate the equation. So now we have v squared r divided by the coefficient of friction. So again, how rough is your coefficient of friction will prevent you from falling. Okay, how rough is your coefficient of friction will prevent you from falling. But how will that roughness be good enough in order to hold you? Then you have to speed up the rotation, and that is at this speed, which is the square root of the ratio between the radius and the coefficient of friction. So this is the minimum velocity to prevent falling. Let me just move my picture over here. So you could see the rest of the solution. So here you go. Hope that this video will help you understand possible questions on rotators.